Hello, everyone. Thanks for joining this talk. So in this presentation, I will talk about how power management works on a Linux system, from the interfaces available in the hardware to the kernel subsystems and the interfaces available to user space applications. So let's get started. Before I start the presentation, a quick introduction about myself. So my name is Sergio Prado. I've been working with this embedded Linux field for 25 plus years now. I have my company. I'm located in São Paulo, Brazil. My company is called Embedded Labworks, and I do consultancy and training on different embedded Linux development aspects, and usually focus on BSP development and usually using open source software. So I do consultants and I have training on embedded Linux development, Linux device drivers development, embedded Android, the Octo project, and so on. I also have a blog, sergioprado.blog. You can follow me. I have social network. You can follow me on Twitter or LinkedIn. And I also have a YouTube channel in case you want to follow me there. I've been doing a few videos about embedded Linux this year. About the content, we will start with a quick introduction on power management. Then we will talk a little bit about how power management works at the hardware level. Then we will cover a few Linux kernel subsystems to manage power. And then we will finish the presentation with some user space applications that we can use to manage power on a Linux system. So let's start with some introduction. Power management is about managing power, right? Consumption on a system. So in the end, the objective is to consume as little power as possible for a specific use case, right? Ideally without affecting performance or user experience or the security, but usually there are some trade-offs, right? And we will talk about this in this presentation. We also might want to ask why manage power. That depends. I mean, most of the times you want to decrease power consumption because your device is powered by a battery. But that's not all of the cases. For example, in data centers where power is very important, powers mean money in data centers. So saving power is very important to data centers. That might be another motivation. You might have some kind of safety requirements, and then because of that, you want to decrease heat in a device, and that might be a reason as well. Or maybe even like some kind of environmental requirement. You want to decrease the carbon footprint for a specific device. So that might be different reasons why you want to manage power on a system. And of course, here our focus is an embedded Linux system. It's also important to understand that there are trade-offs, right? If you want to decrease power, you might be aware that there are trade-offs with performance, right? The more throughput, more power you need. So you might have problems with performance, or it might impact performance if you decrease power on a Linux system. You might also impact the user experience, for example, right? Because of latency. We're going to see that one of the techniques to decrease power consumption is just turn off devices. And when you turn off devices, then there is some kind of latency to waking up that device. So that might impact, for example, the user experience. So we have to keep that in mind. In a computing system, we can say there are three major components involved in power management. We have the hardware, and then the kernel that manages the hardware, and user space applications. So this presentation is separated in three parts because of this. We're going to first start by talking about the hardware, and then we're going to cover the kernel. And actually, this presentation is really focused on the kernel subsystems for power management. And in the end, we're going to talk a little bit about user space application. So let's start talking about the hardware. The hardware is really the foundation, right? Because if you don't have a feature in the hardware that makes it possible to manage power, it's going to be hard for the software to manage the power consumption of the device. That means a few things. First, you really have to design the hardware thinking about it. If you care about power consumption, you have to design the hardware with that in mind. That means selecting components that are power efficient. For example, the CPU architecture. So between x86 and ARM, probably ARM is a better option in terms of power management, in terms of power consumption. x86's processors are usually focused on throughput, on processing power. So you might think about that. Even like a resistor in the wrong place, right, in the board might cause power consumption problems. So thinking about the hardware is very important. This presentation is not really focused on hardware design, but we have to keep that in mind. We're going to focus here, of course, in the software side, but to understand what we can do in the software side to manage power, we have to understand how the power consumption can be managed. And for that, we have to remember this simple equation, right? Power is the product of current and voltage. So if you want to decrease power, you have to decrease current or you have to decrease voltage. We have to keep that in mind because everything that we do at the software level, we are decreasing current, sometimes cutting off current from a device, or decreasing the voltage that we apply to a device. We can separate the techniques to manage power into categories, idle and active. The main difference here is an idle power management technique. It's about managing power when the system is idle or a piece of the system is idle. So for example, the CPU is idle. What you can do? You can turn off the CPU. A hardware is idle. What you can do? You can turn off the hardware. And then as a result, you save power. Usually, idle power management techniques, in idle power management techniques, we have a trade-off between power consumption and latency. Because we have wake-up times, the latency to wake up a piece of hardware. Another category of power management technique is called active power management technique. And this is the case where you are doing something. For example, you have something to do in the CPU, but still you want to save power. In that specific case, for example, you can scale down the CPU frequency to save power. In this case, you have a trade-off between power consumption and performance, right? You decide to save power, and that will impact performance. At the hardware level, there are several, I'm calling here knobs, several knobs that makes it possible to save power. For idle power management, for example, the CPU nowadays, the CPU, they have this, what they call it, the idle state. So sometimes they also call it sleep states or C states. Those are states where the CPU is in power save mode. For example, at the hardware level, you can turn off devices. So there is another technique called clock gating that you can use to just turn off the clock of a device and, as a consequence, save power. Some modern processors, they have this concept of power domain, where several devices that are in the same power domain, and then you can turn them off at the same time. So all of this is provided by the hardware. And then you can, at the software level, you can just use it, right? For active power management, that means you want to manage power at when the system is doing something. There are a few techniques as well. For example, DVFS is a very common technique. Dynamic voltage and frequency scaling is a feature that makes it possible for you to scale down or up the frequency of device, for example, the CPU, to save power. So the CPU is not doing something very important, throughput is not very important, you can scale down the frequency to save power. Because when you scale down the frequency, you also scale down the voltage. And when you decrease the voltage, remember that equation, you decrease the voltage, you decrease the power consumption. Thermal management is another technique because when there is heat generated by a hardware component, usually you have more power consumption. And then if you want to decrease power consumption, you might want also to decrease the heat generated by a device. So another technique. Battery management is another one. If you have a battery, you might want to monitor that battery to make sure that it's in a good state, right? If the battery is getting very, very low, then you might want to decrease, for example, the frequency of the CPU. So there are several techniques that you can apply. I mean, at the hardware level, you need support for this, right? And most of the modern hardware, they provide support for this. For example, on ARM, there is an instruction, FI, that you can use to get a CPU into low power mode, into a low power state. Most peripherals, they have configuration options that you can use, for example, to disable the peripheral and then decrease power consumption. You might have clock controllers connected to peripherals, and then you can disable the clock of a peripheral as a consequence, decreasing power consumption. You might have firmware in the hardware that provides some kind of interface to manage power. That's the case, for example, on x86. Inside the firmware in the motherboard, you have what we usually call BIOS or UFI. Inside of it, we have the ACPI, that one of the responsibilities is to help you to manage power on the system. You might have dedicated chips for that as well. For example, a PMIC chip to manage power on a hardware platform. In the end, I mean, all of those interfaces and features provided by the hardware would be leveraged by the kernel to do power management. Here I have a few diagrams that I took from the reference manual of Citara chip. That's the chip used in the Beagle board, AM335X. And just to see examples, right, on features provided by the hardware, in this case, the SoC for power management. So this is an example of clock gating to disable a device, and an example of power domain to disable a group of devices, and some of the power domains from the SoC. This other one is about the PMIC chip connected to IMX6 SoC from NXP, where you have several regulators that you can control. So with a PMIC, you can connect devices to the regulators of the PMIC and then control the current provided to a device. Then as a consequence, you can turn on and off devices and then save power. Among other things that you can do with the PMIC chip. All right, so this was an introduction about the hardware. Now I want to focus on the kernel and the features provided by the kernel to manage power. In the kernel, we have features to do idle power management and features to do active power management. And we're going to talk about both here. So we have an infrastructure to save power when the system is idle, and we have an infrastructure to save power when the system is doing something. We're going to see that most of this infrastructure and subsystems provided by the kernel, they provide an interface as files. And that's very nice because in the terminal, in the command line, you can manage everything. You don't need special applications or APIs to manage power on the Linux system. You do everything just by reading or writing to files. We're going to see, and I'm going to show you a few examples here. Let's start with idle power management techniques. And while I'm explaining something to you, I'm going to show in the terminal a few things. I have here in my table a board running Linux, a very recent version of the Linux kernel with most of the power management features enabled. So we can try it out in the terminal. So let's start by system-wide power management. So this is a feature that makes it possible for you to get the complete system into a low power mode. That's why it's system-wide. So you can suspend the execution of everything if you don't have anything to do. There are 4 main system-wide power states that you can get the device, from suspend to idle to suspend to disk. The most commonly used here is the suspend-to-RAM. That's what happens when you suspend your Linux system, for example, desktop system. You have also suspend to disk, where the state of the system is saved to disk. Usually we call it this hibernate. And then later you can just resume this from disk. This kind of technique is used when you want to have a fast boot, fast code boot. You can hibernate the system and then boot it up from a known state. I'm going to show you here how suspend-to-RAM works. So as I mentioned, I have here a terminal running. It's a small board that I have here based on an iMac6 SoC from XP. And let me show you here a few things. So this power is a directory where you can do system-wide power management on Linux. Here you have a file called state. You can see here 4 states. Those are the 4 states that I show in the terminal. The main state is the state where you suspend to RAM. So when you suspend to RAM, everything is turned off, but the run itself, the run goes to a kind of a self-refresh state, so you don't lose access or don't lose everything that is in RAM. It's very nice. So now my board is sleeping, and it will sleep forever because right now I don't have what we call a wake-up service. So I will reboot it. But you can see how easy it is to get the system to a low power mode. You just write man to a file, then you suspend the system to run. If you want to wake up, and probably you will want that, right? You have to configure a wake up service. So a wake up service is a mechanism to wake up the system when an event occurs. You can have device drivers registering a wake up service automatically. And you can do that from userspace as well. So let me show you a few things again. So I rebooted the system. I'm going to mount here the debugfs file system, because inside the debugfs file system, there is a file called wakeup service. As you can see, the currently configured wakeup services. To show you something working, I'm gonna configure the RTC, the alarm from the RTC as a wake-up service. I might have the command here. Let's see. Now I'm gonna write again. So I will ask sys class RTC0 wake alarm. So here I'm configuring, let's use 15. So here I'm configuring the RTC to wake up the system in 15 seconds. So now I need to be fast, sleep. So now let's wait a few seconds, in theory 15 seconds, the system will automatically wake up. Let's wait and see. Very good. Just as an example, right? Most of the hardware, they have this power directory where you can control the power of a device and, for example, enable a device as a wake up source. I'm going to show you here another example using the serial port. So sys class TTY max 0 power. So this is the directory where I can manage the power of my serial port, right? And then now I will enable this serial port as a wake up source. So that means every transmission or reception interrupt will wake up the system. I'm gonna get into. So now I'm sleeping, right? I'm gonna press something, wake up the device. So I can have, of course, that depends on hardware support, right? The hardware needs to support that, right? Wake up the system. You have to make sure the hardware support that. So that's the case here. That's why I can use the serial port as a wake up source. And that file that I showed you, you can see, oops, the wake up sources, for example, here, right? That I configured, everything is there. Very nice. So I can get the system to a low power mode to save power. And I can have events to wake up the device. If the hardware support that, I can use that. Another feature that we have in the kernel is called auto sleep or opportunistic suspend. This is very nice because you can just ask the kernel, I want you to sleep, to get into a low power mode, system-wide low power mode, if there is nothing to be done. So by default, the kernel will always get the system to a low power state with this feature. This was introduced by Android, and that's how Android works. It is always sleeping to save power when possible. And but that now it's integrated in the Linux kernel mainline, so anyone can use it. So to use this feature, you go to syspower, and then you have here this auto sleep file that you have to enable. If I do that now, my system will sleep. So there is the concept of lock. There is this wake, lock, and wake unlock file that user space applications can use to let the kernel know if it is the right time to get into a low power mode or not. So if I grab a lock, to do that, I can just write something to this wake lock file. So I grab it a lock. That means the system will not auto sleep. Now, if I enable, so I'm gonna ask the kernel to auto sleep, suspending to run. But since I'm grabbing that lock, right, the kernel will not suspend. As soon as I remove that lock, the kernel will suspend to run. So I can just echo my lock to the wake unlock file. As soon as I do this, the system will get into a low power mode, as you can see. Now the default state is low power mode. Of course, I can wake up the system. For example, My serial port can wake up the system because the serial port I configured it as a wake up source. But look at the difference. Now the system will always sleep. So I press a key, it wakes up, handles the event, and sleeps again. So I can have a system automatically sleeping. The kernel can do that. And have wake up sources configured to wake up the system. So there is an event, the system wake up, it handles the event, and then it sleeps again automatically. This is very nice. What if you want, let's say, for example, you have a system with 4 CPUs. So one CPU is doing something, but the other CPUs, they are not doing anything. You cannot get into a low power mode, a system-wide low power mode, right? Because in this case, one CPU is doing something. But other CPUs, they can sleep. So to make that, to save power at the CPU level, you can use a feature called idle state. So modern processors, they have different idle states. More than one. You might have 3, 4, 5. The deeper the idle state of the CPU, the more power you save. But at the other hand, the more the latency as well. The wake up time is longer. So there is an impact there. Anyway, you can get the CPU into an idle state, a low power mode, right? If you don't have anything to do in that CPU. So the Linux kernel has this subsystem called CPU idle for that. So the CPU idle subsystem, if it is enabled and supported by the hardware, it can automatically get CPUs into a low power mode, into an idle state. Of course, as I mentioned, there are trade-offs between this decision, right? So that's why there are a few algorithms that they call it governors. So here I have a table with the currently available governors, just 3, ladder, menu, and teal. The most used one is menu. I'm not going over the details here. You can read it. It's pretty much straightforward, like the difference, but the algorithms itself, it's a little bit complicated. It's important to understand why there are several different algorithms, because there are trade-offs between going to sleep and waiting for something to happen. If you go to sleep, there will be a latency to wake that up. And that latency might be a big latency depending on the level of the idle state that you want to go. So sometimes it's better to just wait instead of going to an idle state, because sometimes you just have to wait a little bit to do something. And if you go to sleep, then the time to wake up is bigger than the time to wait to do something. So the algorithm, sometimes they must be smart on this, right? And the menu one is usually the one that people use. That's the one that is enabled by the full most Linux system. To check if what is the algorithm enabled on your system, you can just cat this file here. Current governor. Sys device system CPU idle current governor. Here you can see its menu. You can see how many states your CPU has, and then power consumed by each state. The latency to wake up, this is very important. For example, state 1, the latency to wake up is 50 microseconds. That might impact, for example, your real-time requirements. Let's say you have any real-time requirements. But that's automatically managed by the kernel, right? Usually you don't have to do anything, just enabling the kernel, idle, power management, CPU idle, and then the kernel will manage that for you. The only thing that you might want to do here is to define what is the governor that you want to use. Another approach to reduce power consumption is to just get I/O devices into a low power mode. So if you have support in the hardware and in the device driver, you can do that. So you can have a device that is idle by default. That means it will not consume power. And then as soon as you have an event there, the device will wake up to handle that event, and then it will sleep again. Let me show you one example. So I will show you dev bus a USB device, USB bus, sys bus USB, and then devices USB 1 power. So this is the directory to manage power on USB controller 1 of my board. There are several files here. Let me show you a few. For example, auto suspend. That's not the one that I wanted to show. Runtime status is suspended. So the device is at this time suspended. And we have also the auto suspend is the file that has the time to auto suspend the device. So this configuration is 0. That means it will automatically auto suspend as soon as the device is not being used anymore. So at this moment, the USB controller 1 is suspended. It's not consuming too much power. Now I'm going to connect. So I have here a pen drive. I'm going to connect to the board, and we're going to see the difference. Connected, as you can see there. And then now the runtime status is active. That means the device is now active because it has to talk to the USB storage device. As soon as I remove the device, it is sleeping again, suspended. Of course, this is configured. You can configure that. You can enable and disable this feature. But by default, it is usually enabled. Of course, you have to check it, because if you have a device that you can disable, you might want to do that to save power. Remember, that might be a trade-off there, latency, right? To wake up the device. So that is what runtime power management is. All right, so here we have seen a few techniques to do idle power management. You have nothing to do with the system. You can use a system-wide power management technique and get the complete system into a suspended state. You can configure wake-up services to wake up the system. You can have the auto-sleep feature enabled, so the kernel will automatically sleep if there is nothing to be done. You can have CPU idle enabled, and then CPUs that are not doing anything can get into a low power mode, an idle state, to save power. And you can have devices suspended by default when there is nothing to be done with that specific device. So all of those techniques can help you to save power on a Linux system. Now let's talk about active power management techniques. Those are techniques that you want to use to save power even when you have something to do, right? One of the main techniques here is called DVFS, dynamic voltage and frequency scaling. That is a technique that makes it possible to decrease the voltage and frequency of a device, for example, a CPU, to save power. Usually you have some kind of configuration at the hardware level that it is called operating performance points that will be kind of inputs for the system to take decision on what kind of frequencies you can use, what kind of voltages on a specific device. This is usually defined on, for example, a device tree on an ARM-based platform. This is, for example, the configuration on the board that I'm using. This is a device tree from IMX6 Dual Lite, and this is the operating points of CPU 0. You can see that we have 3 different frequencies that I can get the CPU to. And the kernel Linux has a subsystem called CPU freq to manage that. So you can manually define the frequency you want, or you can just use a governor that will take a decision for you. There are 6 governors, so it really depends on what you want to do. For example, you really want to save power, you can get, you might want to configure the power save governor. The power save governor will make sure that the CPUs will be always in the lowest frequency. Let me show a few things here on how this works. Sys bus CPU devices CPU 0 CPU freq. So this is the files exported by the CPU freq subsystem. Here I can see the current frequency, scaling curve freq. I can see all of the available frequencies here. So that's basically what I showed you in the device tree. We can see that it is currently in the middle, right? The frequency. We can also see the governor. Scaling governor. So it is currently using the on-demand governor. So for example, I can change the governor to power save. Power save. Now the governor is in the power save. That means the frequency will be the lowest one, as you can see. I might want to change now the governor to performance. Now it's the highest frequency. The on-demand, it will increase the CPU on demand. So currently, as you can see, is in the middle. For example, let's do some load here. While true, done. Missing a do here. While true, do true, done. Now, I have lots of CPUs doing nothing. And then if we look at the current frequency, it's the highest. Because we need CPU now, because we need things, we need to do things, right? Now, if I kill everything, then the CPU now is in the middle. Because I'm interacting, oh, it decreased again, now it decreased. You can see it's on demand, it depends on what you are doing. It will increase or decrease the frequency of the CPU. So again, you might probably want to leverage that. If you want to decrease power, you might need to decide what kind of governor you want to use. You can decide by yourself if you use the userspace governor, and then you can just select the frequency you want. And you can do that per CPU, okay? You can have one CPU in one frequency and another CPU in another frequency, of course, if that's supported by the hardware. So another technique to manage power on a Linux system. A few more techniques that you can use to manage power on a Linux system, and also related to active power management. Thermal management. As I mentioned, heat dissipation might increase power consumption, so that might also be a problem for safety reasons. So the Linux kernel has a thermal management infrastructure to manage that. You have what they call it thermal zones. That's basically devices that you want to manage heat dissipation. And then you have what they call trippy points. That's basically the thresholds to take decisions. For example, you can configure if this CPU reaches 50 degrees Celsius, then I want to turn on the fan to decrease the heat generated by the CPU. So you have devices, sensors, and actuators, right, in this infrastructure. Here, just an example from my board. I have one thermal zone, that's the SoC IMX. I can see the temperature of the device here. This is the temperature, 53 degrees Celsius. The trip point, it's 85 degrees Celsius. So if the CPU reaches that temperature, it will trigger a cooling device that in this case is the CPU frequency. You turn the CPU frequency down, you scale down the CPU frequency to decrease the temperature of the CPU. So you can just configure that and let the kernel handle it. This is very nice. Power supply is another subsystem provided by the Linux kernel that you can use to manage power supplies, for example, a battery. And that's very important, right? Especially if you have a battery connected to the system, you might want to monitor that. I cannot show you the terminal here because I don't have a battery connected to a device. This is from my notebook, those commands. You can see there is a battery there. I can read the model of the battery. I can see the stats of the battery, if it's charging or discharging. I can see the current capacity, in this case, 95%. So I can really monitor the state of the battery and take any decision in the system, right? If needed. For example, safely turn down the device if the battery is very low. The Linux kernel also has a regulator subsystem that you might want to use. At the kernel level or in user space, the regulator subsystem is designed to provide an interface for voltage and current regulators. So you can turn on off regulators, for example, provided by PMIX and other devices. And as a consequence, you can save power, right? Because if you remove current from a device, you save power. So that's another technique that you can use. This is mostly used by drivers. In user space, you have an interface that you can use to collect information about regulators. There are other features provided by the kernel for power management. For example, modern ARM processors, they have an architecture called Big Little, with processors focus on processing power and processors focus on power consumption. And you can mix that. Of course, you need support in the kernel scheduler to make sure that you use those cores in an efficient way. The Linux kernel has some support for that. All right, I think that ends the kernel part. So of course, there are lots of details here and there, but I wanted to show you a few important subsystems provided by the kernel for power management. To finish this presentation, a few words about user space. The real point here is the kernel provides you several features to manage power, but it's really up to you to use that. You mean as a system designer, when you are designing the system, and your applications, it's up to you to use that. The kernel provides the features, the policies. How you want to use those features is up to user space, not to the kernel. The kernel, of course, it takes some decisions, but most of decisions that are taken by user space applications. So that's important to know. It's you that's going to decide if you're gonna auto-sleep, suspend the CPU, get a device into a suspended state. It's really up to you. You can control and you can configure and decide how you want to manage power. You, as a mentioned assistant designer, you that is designing the system and the applications. Having said that, there are a few applications that you can use to monitor and manage power. PowerTop is one of the most popular. It was developed and designed by Intel. When you run PowerTop, it's going to show you information about power usage per process. That is very nice. Information about idle states, CPU frequency, device state, like what devices are suspended or not. So it's a very interesting all-in-one tool to manage power in a Linux system. Another interesting tool is called TLP. It's sort of a daemon that manages power on a system. So you can use it to make it easier to configure how you want to manage power. There are lots of features available. You might want to check that. Here I have some screenshots listing information about the system, the battery, the processors, devices, and so on. There are other user space features as well that you might want to leverage. My summary for this presentation is you really need to understand the balance between power consumption, performance, user experience. And by user experience, I mean everything that is related to the use case that you are implementing. For example, real-time is part of the user experience. If you have a real-time requirement, it might be impacted by some kind of a power consumption mitigation. So you might want to have that in mind. And then as soon as you gather the requirements and understand what you want to do, you have to define a strategy for power management. Do you want to do idle power management? If so, what kind of idle power management you want to do? Do you want to suspend-to-RAM? Do you want to auto-sleep? What are your wake up sources? Have to define all of that. And what about active power management? Do you want to get the CPU into a lower frequency? You might want to impact performance. Is that okay in your use case? Do you want to manage battery if you have a battery connected? Do you care about the heat generated by the SoC, for example? Do you want to manage that? So everything, you have to keep everything in mind when you are designing this system. So if power consumption is really a need for you, then you really need to think about designing the hardware and the software with that in mind. It's really a kind of system-wide challenge, right? And you need a holistic approach for that. So that's all for today. I hope you enjoyed the talk. Those are my contacts, so feel free to write me an email, follow me. You can reach me easily on LinkedIn. I really hope you enjoyed this talk. Any question, just write me. And yeah, enjoy the conference. Till next time. Bye-bye.